Okay, here I will start from the meter. Here the unit of this for the micro machining. You know very well. Here the 1 kilometer is equal to the 1000 meter, and 1 meter is equal to the 1000 millimeter, and 1 millimeter is equal to the 1000 micrometer, and 1 micrometer is equal to the 1000 nanometer. Here, this is the actual unit. 1 millimeter again here, this is the 1 millimeter, that is the 10 raised to minus 3 meter, and 1 micron is equal to the 10 raised to minus 6 meter, and 1 nanometer, that is the 10 raised to minus 9 meter. Okay, then we'll start the high-speed machinings. The first scientist of high-speed machining, it is proposed by the Carl Salomon in 1931, and he has developed the one modeling technique. As per the conventional machining, here the cutting speed is 5 to 10 times higher than the conventional machining in the as per this high-speed machinings. High-speed machining is too much higher speed, that is a 5 to 10 times that in the conventional machining speed. But in the high-speed machining speed, here we can see the various types of these workpiece material. We can high-speed turning, high-speed milling, or the high-speed broaching machines. Here in the x-axis, that is the cutting speed in the meter per minute, and in y-axis, these are the various types of these workpiece material. These are the transition range and the high-speed range. Here the nickel alloys, here this is the hard and tough material. This hard and tough material, we can maintain the cutting speed up to the 50 to 60 meter per minute. And here the titanium, that is the less harder material than the nickel alloys. But this is the harder material, nothing but. And here the 80 to 90 meter per minute. And the steel material, again, here this is the 600 to 700 meter per minute cutting speed we can achieve. And in cast iron, approximately 850 to 900 meter per minute cutting speed we can achieve. In the bronze and brass, above this 1200 meter per minute, this cutting speed we can achieve. In aluminum, maximum, that is the 1200 meter per minute, this cutting speed we can achieve. And this is but in plastic, moreover, maximum amount of this material removal rate, that is the 13 to 1400 meter per minute. This is the most scenario of the high-speed ranges in machining of various materials, and this is the transition range. But why we are going to the high-speed machinings? What is the purpose of this high-speed machining? What are the advantages of this high-speed machining? When we are going to the high-speed machining, here the accuracy, it will be more and more, and the efficiency of this high-speed machining center, it will be more and more, and reduce the machining time, quality of this workpiece, it will be increased, and the cost of this part piece, here this cost, it will be decreased. And here we can see the various types of this material, this complex shaped parts. We can machine by using the electrode discharge machining or the chemical machining. But here these are the entire cavity we can manufacture by using the high-speed machinings. This is the one improvement of this production when using this high-speed machinings. Here, these are the some features and the prospectus of the high-speed machining. Automatically reduce the heat transfer into the workpiece, reduction of these cutting forces, and increase the cutting speed. These are the advantage of these are the features of high-speed machining. And here the effects. What are the effects of this high-speed machining? Here the part accuracy, it will be getting more and more, surface quality, it will be more and more. Stability of this rotating cutting tool and feed rate, increase the material removal rate. Here the removal rate, material removal rate, here it will be more and more. And what is the comparison of this conventional machining and the high-speed machinings? Right, the contact time between the cutting tool and the workpiece is large in case of this conventional machining, but in high-speed machining, the contact time between the workpiece and the cutting tool material is short, and hence due to this reason, here In conventional machining, it is the less accurate and more accurate than the high-speed machining. But in conventional machining, the very large cutting forces are applied, and in high-speed machining, a small amount of these cutting forces is applied. Due to this cutting force and the cutting speed, here the in conventional machinings, here the surface finish and here the roughness, here this is the poor in case of these conventional machinings. But in high-speed machinings, here the good surface roughness, here it can be achieved, and material removal rate, it is very low in conventional machining speed. In high-speed machinings, material removal rate is higher and higher, and cutting fluid is required, but in high-speed machining, cutting fluid is not required. Right? Again, but we can achieve the dimensional tolerances by using the high-speed machining, that is the 20 micron to near this is the 2 micron, or the in dimensional in EDM, that is the 20 micron. This is the main reason, and there is no need of making cutting tool according to the control to be machined. But in EDM, cutting tool has to be made accepting to the control to be machined. Here the in high-speed machining and the high-speed cutting machine tools, the most challenging, that is the nickel based and titanium and the ferrous alloys. These are the main, but here the activities on this this machining center, that is the turning, milling, and on the aluminum material. Here this is the research is going on for the nickel based alloys. Development for the development is required for the high-speed machinings, for the machining centers, the control systems, tolling, cam, delivery, and the objectives of the machining centers or the high-speed machining, that is the lower cost, shorten time, manufacturing complex and high quality parts to accelerate the product development. These are the objectives. Why we are going this high-speed machining? But some factors are affecting on to these high-speed machinings. These factors here, that is has the workpiece material. If the workpiece material, it has the hard material and the hardness, then it is difficult to machine the part. When this plastic material, it is the soft material, and to machine this part, that is the very less time is required. But the challenging, that is the process capability and the cutting force and the cutting energy, the speed, feed, and depth of this cutting tool. Here the application of high-speed technology. High-speed technology, that is the, but we can machine here the maximum, that is the light metal, that is a non-ferrous material, and the plastic material. We can manufacture this light material, non-ferrous, and the plastic material. But it is difficult to machine in case of steel and the cast iron. But in milling, automotive aircrafts, in automotive aircrafts, that is the thin-walled cylinders or thin-walled plates, and in case of these die molding machines. In forging die machines, the male and female parts, and the injection molding machines, press and press work, die and mold designs. Here the application, that is the, and again we can extend the application in electronics and telecommunication. This is the printed circuit board, and for the drilling operation or the micro drilling operation, this is the micro drilling operation, that is a 0.5 diameter, and the machine, it can be operated above the 30,000 revolution per minute to the 40,000 revolution per minute. This aluminum, titanium, and the copper, this material, it is used in this aerospace and the electrical, electronics, biomedical, defense industries. These are the sectors we are using, and the rapid prototyping technique, this material, hardened steel and molding, mold die for the forging, press and press work, and injection die castings. Here, well, this is the one case. These engine blocks are the gear housing material. We can machine that is the face milling, and this face milling here, it requires the 1,000 to the 5,000 revolution per minute, and this motor required is 10 to 20 kilowatt power. Here, this is on this milling and precise parts in mechanical, electronic sectors. Okay, right? But what are the benefits of the high-speed machining with compared to the conventional machining speed? This material removing rate, that is 5 times greater than the conventional machining speed. Here, automatically, the machining time, it will be reduced 70%. The machining cost, it will be again reduced 25 to the 50%. Productivity automatically, exponentially increase. Here, the high-speed milling results, that is the high-quality surface. In case of the tool, here the tool industry and the die and molded design. In case of forging and the press work operations, injection molding dies. But in traditional machining operation, here this 50%, here this machining operation, here it will be reduced due to the super hard cutting tool material. But in the high speed machinings, super hard cutting tool material, that is the cubic boron nitride, diamond material, or the polycrystalline diamond material, these are the super hard cutting tool materials are used for the high speed machinings. Here the cubic boron nitrides, here the one example, that is if you are milling for the hardened steel, this hardened steel workpiece material, that is the 60 HRC, and the feed, that is the 1000 meter per minute, and we can obtain the dimensional tolerance, that is the 2 micron and reduce the automatically lead time about the 30 to 50%. This is the most important example of these high speed machinings. Here when material removal rate, here the increases surface quality also, and the roughness and the finishing, here it will be increases at the same time, and the cutting force, it will be decreases drastically. But in the high-speed machining, the small amount of heat generated in cutting zone with workpiece and the cutting tool life. Okay, but in ceramic, we can put the 1000 meter per minute because the extreme brittleness. Here, these are the benefits of high-speed machining in relation to the initial investment. Here, these are the technological advantage. These are the 5 technological advantage: large cutting volumes, high surface quality, low cutting force, high frequency excitation, and the heat removal chips. These are the most important challenges, and these are the technological advantages. But in large cutting volumes, the application field, that is the light metal alloys and the steel and the cast iron material, these are the workpiece material, and we can use these different industry sectors: aircraft, aerospace, production, tool, cutting tool, here and the die mold manufacturing industry. Here, this is the maximum amount of these material, it will be removed, and we can obtain the high surface quality, high surface finishing for the precise machining and the special workpiece. And the optical industry, this optical industry, that is the Carl Zeiss, or the mirror, this concave mirror, this convex mirror, or the flat mirror, or the any watches of this small gear, and the precision parts, and the spiral compression springs are there, and the low cutting force, here it will be initiated in the high speed machining when we are going to the thin walled workpiece, these machinings, aircraft and the aerospace production. This is the main industrial application. High frequency excitation, right? Here there is no vibration during the machining and difficult to the machinings. Here, in case it is the application in precise machining or optical industry. Here, automatically the heat removal of the shapes, no warping of these machinings, and this is for the magnesium alloys and the precision machining. Here it will be takes place. Here the high speed machining for the monolithic parts. Here the high speed machining, we are going due to the less cutting force, heat transfer into the workpiece, allowing machining of thin walled parts with high precision. This with high precision, high cutting speed, aerospace industries for the press and press work in sheet metal industry. If there is any fabrication of deep pocketed parts where there is a oil incoming and the inlet and the outlet of this oil, inlet and outlet of this water or any fluid, or in case of this AC, that is the ammonia, any parts of this here, we can manufacture the workpiece, that is the aluminum parts, that is the component, that is a pressure vessel with various complex precision geometry of the for the we know the in pressure vessel and the called neuron vector. Here one application, that is the body of this scanning tunnel and microscope, body from the molybdenum and the titanium plates. This titanium plates for the Kaplan turbine and the Francis turbine. Here we can make the we can manufacture these parts by the high-speed machinings. But for this aluminum parts, thin wall structure, we can go to the 20,000 revolution per minute, and we can do this cutting tool material, that is the end to end mill cutter, and this end mill cutter, that is 118 millimeter long and 11.8 millimeter diameter. This high speed milling, titanium alloy is 13 millimeter end mill cutter, 4,000 revolution per minute. Here these are the various example and the research and development analysis. Here the application of high speed machinings. Here the use of high speed machining, that is to shorten the production time, increase the accuracy of these parts, and these are the different industries. We can use the high speed machining for the medical devices and the automotive components and the aircraft industries, thin walled parts, for the long aluminum parts, die and mold industries, press and press work, and the forging industries, to machine the hard parts with high speed, with high accuracy, and the dies are made of demanding tool steels of the moderate small size. If there is a small size of this component, we can machine smoothly, effectively, and properly. Here are these forging dies for the high speed machinings. Here we can manufacture the thin walled complex shaped parts, and these forging dies here, this is a very hard material and upon to prone cracks. And the injection molds, that is the male and female components, here it is suitable for the high speed machining because the small sizes. And the prototyping of this die and molds material, here this 15,000 to the 50,000 revolution per minute. Here this cutting tool material, the feeds we can give, and the feeds are also very high and cause the reduction of this production process, isn't it? And here we can go to this electrochemical machining as well as the electro discharge machining. And here the cutting tool life here automatically increase the considerably, right? Here this is the one example, one graph. This is the most important graph. Here this is the n-axis, x-axis, that is the cutting speed, VC, meter per minute. Okay. In y-axis, that is the chip removal temperature, But here this is the machinability, how we can machine on the different types of this material. But when we are going to the machine these parts, and what is the effect of this temperature onto this machining condition. See, in conventional machining centers, here the temperature, it will go to the 450 to the 500 meter per minute, and the cheap remote temperature, it will be the 800 degrees Celsius. But when we are increasing this cutting speed of this machining center, 600 onwards. See, in case of the steel material, the temperature, it will be rise. Here, this is the one graph, and this temperature here, it will be 1600, and but the cutting speed, it will be up to the 1600 meter per minute. And again, here but in cast iron material, the maximum here the temperature, again it will be reduced. Still, the cheap remote temperature at the time of the steel, the cheap remote temperature is 1600 degrees Celsius. But in cast iron, the temperature here it will be again goes down. That is the 1300 to the 1400 degrees Celsius. Then next, that is the tungsten carbide. Tungsten carbide, that is the 900 degrees Celsius. Starlight 850 degrees Celsius. But these two materials, it has the again when we are going, that is the cutting speed, it will be drastically decreases. But in case of non-ferrous material, here the temperature, cheap remote temperature, that is the 810 degrees Celsius, but the cutting speed, it will be more and more above the this 2000 to the 2500 meter per minute. This is the most advantages of the cutting speed versus the cheap remote temperature in case of non-ferrous alloys and the non-ferrous material as well as the plastic industries. Isn't it? This is the main application. Next, again, the effect of cutting speed on cutting force. Here, see, in this graph, in the x-axis, that is the cutting speed, and we have taken this one example, the machining center for the 10 kilowatt, and the y-axis, that is the cutting force, and what will happen? The when for the machining center, the cutting speed is 500, 450 to the 500. Here, the what will happen? The cutting force is 2400 to the 2500. Here, this is the too much cutting force is required to machine the parts in case of this 500 meter per minute. But when we are increasing this cutting speed from the 500, 510, 600, 700, 800, 1000, 1500, 2000, 2500, 3000, and what will happen? The cutting force, it will be drastically reduced. This is the main advantages, and there is no aberration in case of this high-speed machining tools. And we can calculate the cutting force equal to the cutting force equal to this here, the load upon this here, this PC upon this VC, isn't it? This is the main formula of this to calculate the cutting force. Here, the effect of cutting speed on cutting force for the aluminum of 7050. This is the one product, and this is the one case studies. Here, in case of the here in x-axis, that is the velocity, cutting speed, and the specific cutting force. But and when machine these parts for these 400 meter per minute, here the cutting speed, it will be the 650 Newton per millimeter square. But what will happen? When the cutting speed, it will be increased, suddenly this specific cutting force, it will be again increased. But when cutting at the optimum time and optimum cutting force, optimum specific cutting force, when again we are increasing the cutting speed for the workpiece material of aluminum, drastically the specific cutting force here, it will be decreased. And this is the main advantages of the high-speed machinings. This is the one phenomenon of this. We have seen the cutting force and specific cutting force and the cutting energy. If there is, and after that, there is no aberration of this and the machine tools. See, here again the comparison of conventional machining with high-speed machining. Here, see, this is the horizontally. Here, the what type of this cutting tools are using, or the workpiece are using. We can use the solid cutting tool material, that is the end mill cutter, or the this is the PCD, that is the polycrystalline diamond cutting tool material, or the ceramic material, or the WC, that is the tungsten carbide material, and this cubic boron nitride material, or the polycrystalline diamond materials. Here, see, when the workpiece material is cast iron, we can see the soft and the ductile. Soft cast iron or the ductile malleable cast iron. Here, these are the different numericals. These are it is found in the research and development technical analysis. Here, the steel, that is again we can classify for the alloy steel, stainless steel, hardness steel, and the different hardness, and we can machine these parts by using the various types of these solid cutting tools and the indexable cutting tools. And the next, that is the hard material titanium alloys and the super alloys. Here what will happen, the mid speed, the cutting speed here, it will be drastically, it will be moving down, that is a 46 meter per minute. The maximum for the cutting speed, that is a 305 for the polycrystalline diamond cutting tools material, cutting tool material, and the tungsten carbide material. This is a 305 maximum cutting speed. It will be obtained in aluminum, and the minimum cutting speed it will be obtained for the tough and hard material and the high hardness material, that is a 46 meter per minute. This is a most important example, but this is a typical cutting speed. And high cutting speed, that is the for the aluminum 3050 meter per minute. Maximum cutting speed it will be obtained for the this tungsten carbide material or the polycrystalline material. This is the maximum cutting speed. But in super alloys hard material, that is a 76 meter per minute. This is the main example. And these are the various typical cutting speed and maximum highest cutting speed for these various types of the indexable cutting tools. Here, this is the 610 to the 3658 to the 46 and 84 and the 366. Here, this is the these are the different types of these speed ranges we can obtain, right? And here we have seen this one example, this graph. Okay, right? Here, this is the what are the machining characteristics for the high-speed machinings. Here, these are the for total 5 parameters, 5 machining parameters. Here, when we are increasing the cutting speed or the decreasing the cutting speed, what will be affect on to this here, this chip volume, surface quality, machining time, cutting force, and tool life material. If you can see the chip volume, that is the material removal rate, that is the cubic volume, that is the when we are increasing this cutting speed, what will happen? The chip volume, the material removal rate, here it will be increased again and again. More and more chip it will be removed. And what will happen? But and the surface quality, here when the cutting speed, when we are increasing, what will happen? The surface quality here it will be increasing. We know very well when the cutting speed is decreases, here the surface quality of this part it will be reduces, it will be minimizes. But surface quality when to increase, the speed should be increased, isn't it? What will happen? The machining time, when the cutting speed again when we are increasing for this workpiece material, the machining time it will be drastically reduced. The machining time it will be minimizes. And then what will happen? The cutting force and specific cutting force, here we have seen. What will happen? Initially the maximum cutting force is required and low cutting speed. And what will happen? When cutting started and when cutting speed, when we are increasing, what will happen? The cutting speed it will be drastically moving down, and here it will be maintained, and here it will be optimized. And here this cutting cutting force, here it will be stagnant, and here it will be same and continuous throughout the machining time. But in case of this cutting tool life, here this cutting tool life, we are using the high speed steel tool material, this tungsten carbide tool materials, or the polycrystalline diamond cutting tool material, or the diamond cutting material, or here these tool life, here what will happen? At the initially when we are manufacturing, the cutting speed is less, and cuttings here the tool life here, that is a more for the less cutting speed, isn't it? Cutting tool life is more for the less cutting speed, but when we are increasing this cutting speed, then what will happen? The tool life here, drastically moving down. Here it will be minimized. But this is the most important challenge, that is the cutting tool. Here the life of this cutting tool should be increased during the machine tool, this high-speed machining center. These are the machining characteristics for the high-speed machining technologies. Okay, but when we are developing these high-speed machining centers, here these are the three main important parameters are required: machine and spindle, tooling, interface, and cutting tools. Actually, these three parameters should be taken into the account. That is when we are manufacturing this machining centers. And the machining and the to manufacture this machine, first that is the main, that is the heart, that is the machine and the spindle. We are using the angular contact bearings, ceramic ball bearings, hydrodynamic bearings, this fluid bearings. And here this first of all we have to design, and these bearings should be rotate and move above the 45,000 revolution per minute, 45,000 to the 80,000 revolution per minute, hydrostatic bearings and hydrodynamic bearings. Here we have to consider these linear motors and the linear actuators and rotary actuators. Linear actuator, that is to shift this tool from this one place to this longitudinal moment, cross moment, and this here the feeding is required, and to remove the heat and the dust and the chip, we have to chip control, and the dynamic stiffness is required. And here the tool changing, that is the magazine. The fast tool changes is required, fast pallet is changing required for the automation purpose, and the high pressure coolant supply is required. Here we are supplying this air as well as this coolant, that is in the form of mist, that is the aerosol. Here it is called as aerosol. And this here such types of the system should be combined with the machining centers and the cell manufacturing and the control systems, the open loop control systems and the closed loop control system. Here this such types of the system should be installed into this machining center. But here we are considering this all this point here, the maintenance should be easy, and here this is a modular part fixturing. Then tooling interface, that is this is the cutting tool interface between this cutting tool and the workpiece material. Here this is but this cutting tool should be clamped uniformly, and here it requires the static and the dynamic stiffness, right? And this cutting tool, that is the repeatability, accuracy, positional accuracy. Here what is the length, what is the diameter, what is the bed, and this is the balance condition, standardization, this adaptability, and the speed limit is required. But in the cutting tool material, this work material, we have seen that aluminum and the speed and the high speed steel, then the super alloy steel, tungsten, titanium alloys. Here these are the material we should take into this account to manufacture the high speed machining parts. And this cutting operation, what type of this cutting operation is required, this face milling or the internal or external. This milling or broaching or the turning, the turning machining center, this milling machining centers or the broaching machining centers or the grinding machining centers. And here this cutting tool material, that is the polished diamond material. What type of these cutting tools are required? What type of these cutting tools are used for the different types of the workpiece material ranges? And how that is this tool management here after the way of this cutting tool, how you can replace after what time, and here it depends on the tool life and the level of this machine tool technology. Here this multi-purpose tooling tools, balancing, safety, and what safety you are giving to the machine tool. Here all these points should be considered whenever we are designing these high-speed machining centers. Here this is the criteria for the high-speed and the high-velocity machining centers. These parameters should be taken into account at the time of. But here this is the stability loop diagram with spindle speed ranges. See, this is the machining, the this when we are giving this proper speed, feed, and depth of this cut. At the initially, what will happen? The in conventional machining center, conventional machining, here this cutting speed, here it will be slowly increasing, and up to this the 2300 revolution per minute, the width and the thickness of the chip removal, that's the cutting chip, the width and the breadth of this cutting chip is maximum. And what will happen, when we are again increasing the speed, that is the 2300 to the 7500, here what will happen, again there is a chatter between this cutting tool and the workpiece material, but above the 7500 to the 45,000, what will happen, the suddenly the width and the length of this cutting chip, here it will be more and more, but what will happen, the speed it will be drastically increases, but the width is less. Again, what will happen, this is the ultra speed above the this 45,000 revolution per minute, and this is the high speed, that is the from this 7,500 to the 45,000, 7,000 to the 45,000. This is the high speed machining, but above this 45,000 to the 60,000 and 80,000, these speed ranges are the ultra high speed ranges, and these high speed machinings and the ultra high speeds are used in this high speed machining and the ultra high speed ranges. Okay, but here the acceleration of this cutting tool material, here to traverse this cutting tool material from this initial point or from the reference point to the base point of this machining. See here in case of this conventional machining center, what will happen, to accelerate the cutting tool from the reference point to the base point of this machining, here this time required is more and more. Time required is more and more, but in high-speed machining center, the time required to accelerate the cutting tool, here it is again less. And this is the high-speed machining center at low end, where these are the two ends are given. High-speed machining center at low end and high-speed machining centers at high end. This is the rapid travel. Here the rapid cutting tool travels from the base point to the required point. Here this is the in meter per second square. Here these are the examples of monolithic components machined at high speeds and deep pocketed aluminum parts for the high speed machining. Thin walled cylinders, we can give the high speed machining above the 7,500 revolution per minute to the 45,000 revolution per minute. Here, this is again one thin walled aluminum pressure vessels for the neuron reactors or this any type of this reactor. This is here it requires the high speed machining centers. Here, this is the standing tunnel microscope. This is the body. It is made up of by using the titanium and molybdenum. This titanium and the molybdenum material, it is the hard part material. This hard part material here it requires the hard high speed machinings. And this high speed machining, this body is made for this scanning tunnel microscope. And this is the turbine blade for this one example. I'm showing the titanium blade or the titanium blade for the Kaplan turbine or the Francis turbine. Right here, this is the surface finish before and after the metal removal rate. This is the one example it is shown. I have taken the snapshots of from the one industry. Right here, this is the one. These are the some elements and the parameters used for the high-speed machining centers, high-speed machinings. High cutting speed machining, we see these are the parameter: high speed speed machining yan, high feed machining F, and this high feed rates with high speeds and cutting specific cutting tools and specific tool motion is required for this high speed machinings. Right here, this is the circular farm tool. This circular farm tool here, this is the how to calculate the diameter of this end mill cutter. Here, this is the these nomenclature. It is given, that is the this AP, that is the step over distance of this cutting tool materials, and this is the velocity of this effective cutting speed by n, and n, that is the cutting speed, and the d, that is the diameter of end mill cutter. Here we can find out from this, if we know the diameter of cutting diameter of this end mill cutter, and then we can find out the effective cutting speed and the feed. Here that this is the f z into this n into this zn millimeter per minute. Here this is the true cutting speed it can be obtained. This here the material removal rate, that is the q. Q, that is the, here I have shown before this graph, that is AP is equal to the vertical distance from the tool tip to the reference point, and AE equal to the step over the distance millimeter, and VF equal to this feed speed millimeter per minute. Here this is the main challenging task. Here the surface finish, it depends on this cutting tool geometry and the coating of the cutting tool. Here we can find out the surface roughness, and the surface roughness, that is the here D, that is the diameter of this end mill cutter, and this AE we have seen, that is the step over distance or the of the cutting tool. Here this is the formula R. This roughness equal to the D by 2 under root of the D square plus AE square upon this port. Right. Here these are the advantages of this high speed machining: high material removal rate, high surface finish, increase the productivity. We can manufacture the thin walled machining and the components. Lead time, it will be automatically reduced. Cutting force, it will be reduced. And when the cutting speed is increasing and the temperature again it will be decreasing. This is the most important research and development analysis technique. And this contact time between the cutting tool and the workpiece, it is the less, and the connection time between the cutting edge and workpiece is very short, and hence it eliminates the need of the coolant and the reduction of this production process. This is the main features and the application and the important aspects of high-speed machining. Right here, this is the but. There is a point we have to consider the disadvantages of high-speed machining. Here the high-speed machining, but this high-speed machining, this cutting tool material, it is very expensive. Machining center, the cost of this machining center, this CAD modeling and the cutting tool material, this is the expensive. And special machine tools, and here it required the advanced spindles and the advanced controllers are required. The relay logic and the various types of this controller, open loop control system, then closed loop control system, various types of the control, then this flow controls, isn't it? And excessive maximum amount of this here the material due to the removal rate. Here the wear action takes place, and good work and the process planning is necessary. It can be difficult to find out and recruit advanced staff. Here these are the most important necessary requirement for the advanced staff. Right. Here the tool holder balancing problem. Here, see, this is the tool holder balancing problem. This is the rotational cutting speed in the x-axis, that is the revolution per minute, and vibration severity in millimeter per second. Then what will happen when the cutting speed it will be increases at at 10,000 revolution per minute? What will happen? The vibration of this machine tool it will be increasing. The vibration severity millimeter per second, here it will be increasing. But at the optimum this cutting force, what will happen? This cutting force and the cutting energy required is less and less when we are going to the rotational cutting speed increasing. Okay, right? Here, these are the applications and the examples and the characteristics of the high-speed machining centers. See, High metal removal, volume, and time. It is used in the light metals, steel, and the cast iron. Example, we are doing the thin walled cylinders, thin walled applications in aerospace and die and mold making, these male and female parts. They tie and the punch. If you are then next character, that is the high surface quality, precision machining, special components are required in the die and molding in the industries as well as the optics and precision mechanics, watches, and the optical industries. And the when and here the low cutting force, high exciting frequency, heat dissipation through the chips. These are the various characteristics, thin walled components and the vibration free machinings. And these different types of these sectors we are using in the for the high-speed machining centers, aerospace industries, automotive industries, household appliances, precision components, optical industries, magnesium alloys. These are the examples for the various types of the applications and the characteristics. Okay, right. Here the high-speed machining is high productive machining and small size the component in roughing to finishing and in finishing to the super finishing, right? Right. Here but these high speed machining centers, high speed this machining, it is used for the only the small size the component, not for the large size component, and hence this high speed machining is known for the long time, and research are still being developed for further improvement and quality and optimization cost. Here, this is the main challenges in the high speed machinings, right? Here, the machine details, we can see the what type of these machines are required and what are the these parameters and what are the specifications are required. Here, if you take this one machine tool, that is a 3-axis horizontal and the vertical milling machines, one machine tool that is a CNC 4-axis, and the CNC that is the 5-axis machine tools, and the tilting of this 4-axis machine tool, that is we can tilt this milling cutter. Here, the tilting of this milling cutter to improve the cutting conditions. And in the 5-axis, this machine tools, that is a changeable spindle units. There, the changeable spindle units mean what? They are the two for the rough finishing, the semi-finishing, or the final finishing in single step. Here, this is the 5-axis machining center. For the you can use the 4-axis machining centers and the 3-axis machining center. These are the different types of these machine tools are available in the market. See, one example I have taken this one industry, that is the Hulko. This type of this machining centers, this machining, it is used for the 18,000 revolution per minute, and cement cutting tools they have used, and they have used this hybrid bearings and high-speed integral motor spindles, and here this is the turbo machining is based. Here the specifications used for this machining center, the table size, the maximum weight on this table, the speed, spindle motor, screw capacity, maximum tool diameter, maximum programmable feed rate, rapid driver, that is to the X, Y, and Z axis, required the floor space. How much that is the floor space is required, we have to consider this into this account when we are manufacturing the high-speed machining centers, right? Then again, here the how much that is the pallet of holes, peak spindle speed motors, and what type of this cutting tools are required, how much cutting the tool diameter, and how much that is the cutting tool length, and what is the weight of this cutting tool, and it is the programmable or not programmable, how much to be rapid transfers, and how to accelerate the cutting tool from the reference point to the base point. Here, these points should be considered into this specifications of cutting tools. Here, these are the specific cutting tools are required. That is the titanium nitride or the titanium carbide, Then the next, that is this titanium carbide nitride, that is the 42 hardness material. This is the Rockwell hardness, 42 Rockwell hardness, and the titanium aluminum nitride. Here, this is the coated carbide materials. Here, the hardness, that is this Rockwell hardness, that is the 32 and above. For special applications like hard turning, that is the 60 to 65 Rockwell hardness. And we can use this material, that is the cutting tool material, the polycrystalline boron nitride, and the cubic boron nitride is CBN, and the ceramic for the cast iron. For the ceramic cast iron material, we can use the cubic boron nitride materials, and for the aluminum materials, we can use the polycrystalline diamond materials and the ceramic. Polycrystalline diamond materials and ceramic materials are used for this aluminum, right? Here, these are some workpiece materials, and here the coatings are required on this cutting tool material. And tomorrow, cutting here some coatings are applied onto this cutting tool material. See. Hello. 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 This workpiece material, that is the steel and stainless steel, cast iron, non-ferrous material, and the heavy duty material. These are the various types of this material we can use into this workpiece material. And the coating applied onto this cutting tool material, that is the titanium nitride, titanium aluminum nitride, titanium. Here, this is we can apply this. We are in current scenario, we are applying this coating onto this cutting tool materials by using the vapor deposition technique. But in the tomorrow, we can apply the aluminum oxides, and this is the super nitrides, and diamond and titanium boride and super nitrides. These are the most important challenges. How to coat this material onto the cutting tool material by the various coating technique. Here, this is the most important application, right? Here, this is the one conclusion for the high-speed machining. This high-speed cutting speed should be regarded as operations performed. High-speed machining is not necessarily high-speed machinings, but here we can go to these cutting fluids. Not cutting fluids are required for these high-speed machinings. Here, in high-speed machinings, here it requires the cutting fluids. The purpose of this cutting fluid is removal of this cutting, removal of heat generated during the cutting, removal of the chips, reduction of this cutting tool wear, better surface finish. For this purpose, we are using the metal working fluids, isn't it? And here this coolant system. This cutting fluid, the flow. Here this is the maximum 15%, and the cost of this machining for the high-speed machining. Here it requires the automation, that is the 8%. Foundation of this machine tool, that is a 6%. Building floor space, it's the 6%. Scrap 3%. Retool 6%. Availability of this series component 10%. Maintenance service 12%. Machine capital cost 26%. Energy required for this machine tool, that is a 4%. Cutting tool, that is a 4%. But in all this, here this criteria, this 15% coolant system is required. Here this is a total this costing is considered in this automation production system, right? Here this is the gears. Here these two gears are applied. Here this coolant and the lubrication is to be applied in between these two gears. Here this is a metalworking in industry. Here this coolant and the lubricant, here it will be into the cutting tool interface and the workpiece side. Here then oil or the cutting flow, it will be supplied. Here this is the maximum utility of this machining center. Here why this cutting fluids is required. Here this lubricating cutting process at low cutting speed with cooling the workpiece at high cutting speed and to flush these cutting chips from the cutting speed. This is the main aspect of this cutting fluids and machining, right? Here uh, if we are not giving this cutting fluids or if we are not lubricating how the part is, here the urinate and corrodate. Here this is the one example it is I have shown. And next that is what type of this lubricating oil or the coolants. Here it will be applied. There are the 4 types of these cutting fluids are required for the high-speed machining. This is a straight oil, soluble oil, semi-synthetic fluids, synthetic fluids. These are the 4 categories of these oils are required for this high-speed machining. You can go anywhere, but here you have to maintain the properties of this cutting fluid. Here this cutting fluid. What are the properties of cutting fluid? Here this cutting fluid. Here to reduce the frictional force between the workpiece and the cutting fluid. And this cutting fluid, it should be non-toxic. It should be chemical inactive. It should be easily not flammable, and it should be stable in use and storage and high heat conductivity. These are the most important properties of cutting fluid, and we have maintained all this property to the cutting tool, this cutting fluid, and here the automatically what will happen, the cutting tool life it will be increased more and more. Right here, this is the one jet application of this fluid. The jet of cutting fluid is applied on the workpiece. Here this amount of this cutting fluid here it should be initiated through the nozzle at the edge here at the point of this cutting tool interface and the workpiece. Right here, this is the mist lubrication method. This is the aerosol method. Here, this is the cutting fluid atomized by a jet of air. This is the one. These are the 2 pipes we have seen. This is one pipe that is the air is coming, and other is that is the oil is supplying. Through this air, what will happen? We are removing the metal chips, and here this pipe here the oil or the coolant flow here it will be supplying from this other end. These are the 2 pipes are connected for the conventional machines. But here what are the benefits and why we are using this cutting fluid? Here the tool life here previously I have discussed. Here by using this proper cutting fluid, this cutting life it will be improved, and the cutting force it will be lower and lower. This cutting energy, specific cutting force, it will be increasing. It is lowering when we are increasing the cutting speed. And the maximum surface roughness here, the surface finishing here it will be improved, and this finishing surfaces it will be protected from the corrosion and the erosion. These are the to avoid the erosion and corrosion, the proper this coolant and the fluids we have to select for the machining operation. Here this cutting fluid here the friction wear and the lubrication. Friction, wear and the lubrication. Friction wear and the lubrication. And here these are the main important criteria for the cutting fluids for the better quality of the parts and tool wear, and we can manufacture the hard material at high speeds can be machined and less heat generation and facilitates chip disposal. Here the to remove the chips or to dispose the chips and to here the less heat to generate the less heat. And here these are the most important advantages of these cutting fluids, right? And the function that is the cutting fluids for the high speed machining. Here when we are using this proper type of this proper type and proper amount of these cutting fluids, here the friction it will be reducing, and when heat will be generated here and automatically the heat will be the heat generation it will be reduced, friction it will be reduced, and heat generated here it will be dissipated due to the plastic deformation of this metal during the machining operation. In case of this forging operation, in case of this rolling operations, and the metal forming and the mold design technique, here this plastic deformation technique it will be tested, and we have to supply the proper amount of this coolants and the coolants to supply the proper amount of this coolant and at the interface of this cutting tool and the workpiece, and to increase the cutting tool life and to cool the work for preventing thermal distortion of this work. Here to avoid the thermal distortion of this work and to cool the work and to maintain the temperature of the work at the time of this machining, here the proper lubricant to be supplied and to lubricate the part and to reduce the friction and the important transport function for this removal of the chips. To remove the chips here, to clean the space of this machining. Here, these are the functions of lubricants are used in the high-speed machining, right? Here, I have discussed the cutting tool life it will be increased and the economical cutting speed here it will be contributed. But here the disadvantage. There is some disadvantage in any criteria of any elements. Here there is a economical reasons and the environmental reason. Here in today's scenario, here the use of this oil, here it should be here to minimize the oil and the machining and for the environmental purpose and for the economical reasons. Here we should go to the dry machinings. Here the dry machining again, and there is a next disadvantage, that is the skin exposure, aerial exposure, engagement, and the bacteria. These are the these points are affected on due to the improper selection of this cutting fluid and the lubrication. Here, these are the disadvantages of the these are the demerits for the workers. These are the various 3 routes for the cutting fluids, and hence here the dry machining we use, and the cutting fluid, that is the major source of this. This is the waste generation and the environmental damage, and to eliminate this hazardous cutting fluid during the machining operation, right? This is the cutting fluid is nothing but this is hazardous. This hazardous cutting fluids we have to prevent this, and the researchers have tried here to eliminate and to prevent the uses of hazardous cutting fluid during the machining operation and without applying the cutting fluids, which is known as the dry machining. Here the dry machining, that is we have to prevent the use of oil and the coolants. Here this is then these major problems with this conventional process, that is this corrosion and contamination of the lubrication systems, need of storage, additional floor space, pumping system, recycling and disposal, environmental pollution of health hazards. These are the main points should be considered during this high-speed machining for the coolants. Okay, right? Here the dry. What is the meaning of this dry machining and the semi-dry machining? We have eliminated the use of this oil and the coolants and lubricating. Here there are mainly 3 types of these strategies and the categories. We can supply the fluid type this oil into this machining, and second that is the minimum quantity lubrication, and third that is a dry fluid. Here, okay, the dry fluid can be if it is useless. Here if not delivered efficiently at proper pressure. Here we have to maintain the proper pressure, proper temperature. We have to deliver this oil at specific position at the interface of this cutting tool and the workpiece by positioned nozzles and the filtering system. Here the clean and pure oil here it will be supplied to the system by using the hydraulic power pack, isn't it? And here the function that is the to reduce the friction and absorption of heat and to evacuate the chips. Here the consequences for the work is why is this? For the dry machining operation, lower dimensional accuracy. Here to deteriorate the surface finish, additional cleaning, and to avoid this. Here these are the sub points we have to consider. If the oil is not here, this supply at the interface of this workpiece and the cutting tool, what will happen? Tool life it will be decreased. Severe adhesion takes place between the workpiece and the cutting tool material. That here the chip formation it will not be takes place, and temperature we can't be controlled, and the tool cleaning is required at the need of the extraction. Machine tool, chip disposal, and the chip temperature. This cleaning and sensitive coolant process in case of the grinding, honing, burnishing, and the electro discharge machining. Because what will happen? Here the small amount of this here, the material removal rate, here the dirt, dust, and the chips. Here it is formed, and such type of the dirt, dust, and the chips. Here it should be cleaned from this machining centers and replaced by the this competitive process. Geometrically defined cutting tools successfully without machining fluids. Here these are the dry machining and the semi-dry machinings. Here again the dry machining operation. This minimum quantity lubrication it is used in the I earlier said the flood type cooling lubrication system and the minimum quantity lubrication. But in flood type lubrication, that is the 50, 100 to the 500 milliliter, such types of this here, this is the oil and oil it will be wastage. But in minimum quantity lubrication, that is the 10 to the 100 milliliter, this much amount of this oil it will be supplied. Here it is called as the minimum quantity lubrication. Here then again aspect, here we are using the cast iron material for the machining, but instead of this this aluminum, why this cast iron it has the highest machinability against the aluminum, because the properties of the material, that is this aluminum, it has the high temperature conductivity, and the aluminum absorbs more heat generated during the machining operation. It promotes the workpiece deformation resulting from thermal expansion, difficult to cut, dry conditions. But in cast iron, that is the short chips, low cutting temperature, and lubricant effect of graphite. Here, these are the applications. These are the advantages of this cast iron materials against the aluminum, right? Here this dry machining operation, this dry drilling. This dry drilling, here this carbide drill. This is a serious difficulty of the heat dissipation and the transportation of chip. Here this is the most important, and the drilling of this grey cast iron yields the tool life, and here the ductile iron. This is the tool life. It will be decreases up to the 25%. Here the next that is a fuzzy drilling. Fuzzy drilling is the more reliable, effective, and the minimal coolant, isn't it? And the dry reaming operation, here the dry grinding and the dry honing operation. Here they are using the polycrystalline diamond cutting materials or the cubic boron nitride material. Here we can achieve the surface finish up to the 3 micron to the 9 micron, isn't it? And the thermal problem, that is the for the carbon and the elastic material. Here, these are the some features of dry machining operations, right? Here the workpiece temperature, it will be decreased from the 1110 degrees Celsius to the 65 degrees Celsius at 400 meter per minute and high productivity. And in dry operation, dry boring operation, one example it is taken. Diameter, if the boring tool, that is the diameter is 8.5 millimeter and the length of the boring tool is 25 millimeter, velocity is the 90 meter per minute, field is 0.2 millimeter per revolution, and the standard deviation, that is the plus or minus 5 micron, and this is the bottom of approach, and the top 5, that is the 5 micron. If we are using the ceramic tools and the workpiece, that is the 1045 steel. This is one operation for the dry boring operation, right? And when you are using the self lubricating coating tool material, here this coating cutting tool material, that is the tungsten carbide carbon, chromium carbide or the chromium carbide carbon. Next, that is the titanium nitride plus molybdenum and desulfated titanium and molybdenum sulfate. This MoS2, that is the molybdenum sulfate. Here, this is it can diminish flank wear of this milling cutters. Here, the to achieve to maintain this cutter life of this milling machine. Here, we can use this milling cutter, that is the tin plus molybdenum and this sulfate material. Here, these are the we can achieve the maximum amount of this cutting velocity and the cutting fluids, and this is a feed. Here, for the 20 millimeter of speed, this drilling is 450, and when you have to use the spiral fluted carbide cutting tool material, titanium, aluminum nitride, and the ceramic drill tool material, titanium, aluminum nitride coated carbide drill tool material, manganese, and this BSS. Here we can use this magnesium machine this dry casting tools. One example it is taken for the drilling of machining by using this. Here, this we can use this cutting tool, that is polycrystalline diamond cutting tool material. The cutting speed, that is the 16,000 to the 22,000, and diameter of this drilling cutting tool, that is the 4 to 13 millimeter, and the feed meter per revolution, that is the 0.3 to 0.5 meter per revolution. These are the main advantages, right? Here, but we have to consider again for the dry machine tools and the equipment. But there is a problem to remove the coolants from the machining. To remove the coolants from the machining to control thermal stress, and the dry drilling and the carbide drilling. This is a serious difficult. That is the heat dissipation and the chip formation. This is the main. But the challenges. What are the challenges into this dry machining operation? The main issues, that is in dry machining, that is the tool life, geometrical accuracies of this workpiece, surface integrity of the workpiece, machinability of this material. Here, these are the challenges are occurred into this dry machining operation. Here are some challenges again the tool life. Here the average temperature near cutting tool and workpiece, that is the heat retention in workpiece material, and retain the heat cause the thermal deformation, right? Actually, what will happen due to the dry machining, heat, it will be retained into the workpiece, and the heat cause due to heat cause, here the material it will be deformed, machine part it will be deformed, and this is due to the thermal deformation takes place. And next, that is the workpiece surface integrity. Here, this is the excessive heat built up during the dry machining, and the temperature of the layer to level where this as per the metallurgical, this phase transformation and the microstructural alteration, here it will be increased. and it will cause the formation of hard layer on the surface. Here, this hard layer, that is the white layer, it will be seen from this machining operation. Why it is this white layer and the hard layer? Due to this here, due to the deformation of this workpiece material, the thermal deformation of this material, and due to the heat retention into this work material, these due to this defects, here the white layer or the hard layer is obtained on the surface when you are viewing through the microscope. This is the workpiece surface integrity. This is the most important challenges and the dry machining operation, right? Again, the strategy and the solution for the successful dry machining. Here, what type of this cutting tools are material, what type of this cutting these tool coatings are used. This hybrid machining, that is the here the with and without the coolants, and the minimum quantity lubrication methods. We have to use the cryogenic machinings, undercooling machinings, intercooling by vaporization systems, thermoelectric cooling system. These are the most important parameters. Here the most commonly used in engineering application, that is this austenitic stainless steel, cast iron, nickel, titanium, copper, aluminum alloys, and these elements exhibit the machinings. Here the excessive generation of it. Here these material and the high interfacial temperature. I just the maximum temperature, and the due to the here the heat retention and the heat generation, and due to the temperature increasing and heat generation, here it will take place, heat retention it will be takes place, and this microbiological and the microstructure, this white layer it will be appeared above this layer of this workpiece or the machined part. This is the main challenging task during the dry machinings. Here these cutting tool materials, most here these cutting tools material used in the dry machining, that is the tungsten carbide, titanium tungsten or tantalum tungsten, and ceramics, cubic boron nitride, and diamond materials. These cutting tool materials are used in the dry machining to retain hardness at high temperature or hot hardness, able to resist high stresses. This is the main challenging task in the dry machinings, right? When we are using the carbides of tungsten and titanium, and the grain size, that in the when we are manufacturing the cutting tools by using the powder metallurgy, here these powders are compacted, and the grain size in the range, that is a 10 micrometer to the 1 micrometer. Even the temperature it will be rising. Here the high hardness and the wear resistance, here it will be tasteless. The friction it will be tasteless. But it needs the lubrication. But we are going to the dry machining. There is a no coolant and the low lubricant. And here due to the retention of this heat and the heat generated, then white layer is obtained. Here the ceramics, when we are using this cutting tool, that is the ceramics or the ceramic, due to the withstand the higher temperature and retains the sharpness of the cutting edge, and then for the long duration at elevated temperature. Here the temperature, when the cutting time it will be increasing, and retain the sharpness of this cutting edge and high hardness and wear resistance, but it is suitable for the high speed dry machining. When we are using this cubic boron nitride, harder than the cemented carbide and ceramics at high temperatures. At high elevated temperature, we are using the ceramics and the cemented carbide cutting tool materials due to the high wear resistance. These are the main applications and useful parameters of cutting tool material. Next, diamond. Diamond is the, you know very well, this is the hardest material and it has a high thermal conductivity, high wear resistance to abrasive, isn't it? Here I have taken this one snapshots from the one cutting tool industry. Here the see in x-axis that is the temperature and in y-axis that is the hardness. See what will happen here, this single crystal diamond that is above this 7,000. This is a hardness. Here it will be achieved up to the here this 900 degrees Celsius. This from a single crystal cubic boron nitride. Here this temperature that is the 6,000. But 6,000 hardness is more and more. This the most hardness of this single crystal diamond. Then next that is the single crystal cubic boron nitride. This is the 6,000 hardness. This single crystal cubic boron nitride, the temperature it will be go around 800 degrees Celsius, right? And the next cutting tool, that is the polycrystalline diamond cutting tool material. This polycrystalline diamond cutting tool material, here it will be up to the 6,000 or the 5,600, 5,900 degree, 5,900 is hardness. And next, that is the you can use the aluminum oxide, this cutting tool, or the tungsten carbide, titanium nitride. Titanium nitride, this coating tool coating is applied onto this this tungsten carbide material. Then the next, that is the high speed steel, and the next that is the carbon steel and the cast cobalt alloy. Here these are the different type of the temperature ranges for the hardness. Here this is the most important this graph. We can use this. And the tool coating, what type of this tool coatings are used for the to compensate for the lubricating effects of this cutting tool? Titanium nitride, titanium carbide nitride, and chromium nitride, cubic boron nitride, and the diamonds. These materials are the self-lubricating coating, and cubic boron nitride and the diamond nitride. Hybrid machining, that is the vibration assisted machining, laser and the plasma assisted machinings. Okay, these are the hybrid machinings. Here the minimum quantity lubrication. Here the see, this is the minimum quantity lubrication. Air, the air, that is oxygen, plus here this is the lubricant. Here it will be applied at the end of interface between the cutting tool material and the workpiece. Here see, this is the small amount. Here this is the black spot. This is the, you can say, this is the lubricant particle and the distance between the two particles, that is the air. But here see, that is in conventional machining center, there is a no air gap. This is the dark cloud of this oil. Here it will be applied. That is the 500 milliliters of this oil. It will be supplied. That is the milk. Here this is the useless, and this oil. This costing is more and more in the conventional machining centers. But in minimum quantity lubrication, that is the 10 to the 100 milliliter per hour. This is the main advantages. 10 to 100 ml in per hour. But in conventional, we are using the 50 to 500 500 ml. Here, this is the 5 times. That is the oil. That is the wastage. This is the wastage. How to recover this? Here, this is the advantages of this minimum quantity lubrication. Then we can go to the dry machining, into the cryogenic machining. This cryogenic machining, that is the low temperature refrigeration systems. Cryogenics means what? This is the liquid nitrogen at the low temperature means what? That is the this cryogenic machining. It will be applied at minus 196 degrees Celsius, isn't it? This machining with liquid nitrogen. Here the liquid nitrogen evaporates into the air, and it will be contacted to the cutting tool and the workpiece. And but there is a no harmful this nitrogen. There is a no harmful agents, and it provides excellent cooling effects in machining due to very low temperature. Right here, and hence due to the very low temperature and excellent cooling effects, here this cryogenic, this fluid, it will be used for the cryogenic machining up to the minus 196 degrees Celsius. This is the main important aspect of this. Here cold machinings, right? And under cooling system, the coolant flows through the channels. This channels means what? This is the air channel and the oil channel. These air channels and the oil channel. These two channels are fixed. Here this is the mix. Here it is in the form of mist, or here it is also called as the aerosol. And under this mist, it will be supplied through the nozzle, isn't? And at the cutting zone system. And the internal cooling system by the vaporization system. This vaporization liquid, vaporizable liquid is introduced inside the shank of this cutting tool, right? This is again when this cutting tool, when the cutting action takes place, and through the shank of this internal cutting tool, here to cool this material, here this vaporizer cutting fluid, here it will be supplied but due to the heat generation at the tip of the nozzle of this cutting fluid, and this cutting fluid, it will be dissipated. And here this is the main advantages of this vaporization system of this during the dry speed machining, right? Then the thermoelectric effect. The thermoelectric effect, that is the this at the cold junctions and the hot junction of these two ends. Here this cutting temperature, here it will be suppose for the dry machining, this is the 700 degrees Celsius for the dry machining, and the weight machining, that is the 500 degrees Celsius, and the minimum quantity lubrication, that is the 490 degrees Celsius. These are the flood, and the fourth, that is a flood type lubrication. Dry, weight, minimum quantity lubrication, and the flood type lubrication. But here this is the dry and weight and minimum quantity lubrication we have to consider, right? This application of this dry machining technology, what type of this workpiece material are used in dry machining and the semi-dry machining conditions? Magnesium, the first, the useful material, that is this friction free and this erosion free material, that is the magnesium alloys. Copper alloys, here this is the high thermal conductivity. Cast iron, that is the high machinability property. Aluminum alloys, high cutting speed we can obtain. Aluminum alloy steels and the nickel titanium alloys. Here this is the hard and tough material. Here this is the such types of this material we can use for the application of dry machining technology, right? Here we can use this minimum quantity lubrication for the different types of this machining process. This machining process, it would be the milling operation, dry milling, dry turning, dry drilling, dry grinding operation. These are the different types of these dry machining centers, and we can eliminate the harmful cutting fluid. These harmful cutting fluids we are eliminated during the minimum quantity lubrication, that is the MQL, right? And this cost involved in purchase, storage, handling, utilizing safe disposal of this on the fluid, and the high cutting speed can be achieved, and surface finish, it will be improved, and the reduction in overall production time and the working condition, it will be improved. This is the main advantages of the minimum quantity lubrication, right? Here earlier I said the maximum, that is the 50 to 500 milliliter per hour, and this is a flood cooling. But in near dry lubrication and the micro lubrication, here the 5 to 10 milliliter, here the such types of the lubrication is required. Here this is the for the lubrication purpose. Here we are using these oils or the coolants, these fluids. This is the biodegradability. This what is meant by this biodegradable? You know very well. You know these things here, but on one sentence here, the two there is a no harmful. If there is any harmful these harmful components here, it will be broken down on the this and this harmful defect of this component will be broken down, and hence it is called as the biodegradability. And here the oxidation, here it will not take place. This here the stability will be maintained. There is a no toxicity. These are the various types of these lubricants are used in the minimum quantity lubrication. Then the MQVL, there is another one concept, the minimum quantity volume lubrication is purpose. And the types of these lubrication, that is the synthetic esters, vegetable oils, polysoluble white oils, polyalkaline, then mineral oils, polyol esters A, B, C, D. These are the different types of these molecular weight percentage and biodegradability percentage used in this cutting fluids. These are the fluid selections for the minimum quantity lubrication. Here, see how to supply this minimum quantity lubrication externally or internally. Externally means what? Here this is channel 1 and channel 2. There are 2 channels, and here the one channel. Here the oil it will be supplied through the pump, and the second channel, here the oil it will be injected towards the this cutting point interface and the workpiece point where there is a machining action takes place, and the oil supply here it will be smoothly continued into the supply systems during machining. See, this again one minimum quantity lubrication unit. This is the one external system is provided. External system here it is the combined system of this hydraulic and the pneumatic system. See, first that is the in compressor. This compressor it is the we can store this maximum amount of this air, but this air it will be dry, humidified air, and here this is the hot air, but this hot air, humidified, and this air here it will be cooled, and the pressure it will be come down to the 6 to 8 bar pressure. Then here the FRL unity is placed. This friction, this filtering action takes place. Due to the filtering here, this in the environment, dirt, dust, here this particle it will be removed. This dirt dust particle here, see you know very well this coarse grain size filter, this fine grain size filters are used in these filters, and the air, this oil it will be air it will be lubricated, and this pressure of this air it will be regularized, and through this here the proper the FRN units or this filter regulator at here the air pressure 6 to 8 bar pressure here it will be supplied from this end. Here the cutting fluid, this cutting fluid here here there is a pump. This pump, that is the positive displacement pump is placed, and the output shaft of this pump is connected to the small size of this motor or the battery. Here when it will be started, what will happen? Here the cutting fluid, the clean and pure amount, here the oil here it will be supplied from this air, and the clean and the pure air here it will be supplied from this air, and this air and the oil here it will be coming to the one chamber, and this air and the oil it will be mixed, and here the mist mix this is in the form of mist or the aerosol. Here it will be supplied in the form of this minimum quantity lubrication, and we can check the here the entrance this pressure and here this exit pressure, and this mixture of this air and this lubricator, it will be supplied through the nozzle at the end. Here at the interface between this cutting tool and the workpiece, and this is the tool holder is there, and this is the workpiece, and this is the external minimum quantity lubrication unit. It is connected behind the machine tool. This is the most important. This is I have taken this one snapshot from this journal of this science, right? Here, this is the one again one. There is a snapshot. See, this is a compressor, and this is the one hydraulic power pack unit, and this pneumatic power unit. And here it is coupled with this minimum quantity lubrication. How it is? See here this compressor. Here there is a one direction control valve. Pneumatic. This is the direction control valve. This is a solenoid type direction control valve, and this is the through this. What will happen? The air, this air, it will be supplied, and the air, it will be again this hydraulic, this oil, it will be supplied to the sound. And what will happen? This oil, it will be regulated by the pressure compensated flow control valve. When the pressure at the end of system, it will be increased, then what will happen? This plunger, it will be moved down, or the plunger, it here to move up and to move down and regulate the flow of this oil, regulate the flow of the supply, and the air and the oil here, it will be mixed and it will be regulated. This regulated air and the oil, it will be supplied to the ejector nozzle and through this unit and towards the workpiece. And here it is called as the aerosol control unit. This is the most important application of this dry machinings. Here, this is the one unique method. Generally, this particular machine, this external minimum quantity lubrication unit is placed, right? And here we have discussed this figure previously. See, then this is the one application area of this dry lubrication. When we are going to the workpiece material, suppose the aluminum or the steel or the cast iron. Here, suppose in aluminum, that is the cast aluminum alloys. This is the cast aluminum alloys, or the wrought aluminum alloys, or the next, that is the high-speed alloys, or the bearing steel. Then free cutting steel material. Then quench and tempered cutting steel material, and the gray cast iron material. Suppose the workpiece here, the machining, here the drilling, reaming, the drilling, reaming, and the tapping and the thread forming. Here for the deep hole drilling, this for the aluminum material, here aluminum, steel, and the cast iron material for the drilling, reaming, and the tapping thread forming and deep hole drilling. We are using the minimum quantity lubrication. But for the steel, only steel, that is the free cutting, that is the dry machining, it will be used, and cast iron. But for the milling, turning, gear, milling, swaying, broaching, these 4 machining methods, if you are going towards the steel and the cast iron, here milling, turning, gear, these only three process, you should go to the dry machining operations. Okay, right? Dry machining operations, and remaining, that is the swaying. Here you should go to the minimum quantity lubrication. This table, it indicates the for which process and what workpiece. Here we have to select the minimum quantity lubrication or the dry the machining. What type of this system should be preferred for the different types of this cutting tool material and different types of this workpiece material. This is the main criteria for the during this dry speed dry machining of this high speed machining, right? Here these are the different types of these cutting chips. These cutting chips, that is the in the form of different feed, that is the 0.1 millimeter per revolution to the 1.25 millimeter per revolution. See what will happen here, the feed when we are increasing, then what will happen, the here the feed, that is the width of the chip, it will be increases. Here the dry lubrication and the wet lubrication and this MQL, that is the minimum quantity lubrication. What will happen, the this smooth and continuous this chip, it will be formed, but in the dry, that is the straight and the maximum size here this cutting this the chip, it will be formed, but in weight, that is the curly or the spring type chip, it will be formed the what at different speed and the different cutting velocity. Here we can see the what type of this cutting velocity and the what type of this cutting feed. Here the types of chip formation takes place during the here the machining high speed machining operation. This is the machine tools and the manufacturing. I have taken this data. Here the see, we have also explained that this dry machining operation, this tool material and the tool coating. This tool coating, here the titanium nitride, titanium aluminum nitride, laser cut, and these are the materials. These are the materials are used for the coating the material, and the chip removal using the spindle air. Here the I said earlier, 80 to the 100 pounds square per inch or 6 to 8 bar pressure, air pressure is required for this machining operation, and more than that, here you can remove the chips through the spindle air, right? Here, but here the disadvantage of the dry machining. What are the disadvantages? Here the friction and adhesion between the chip, cutting tool chip, and here it will be higher, right? Friction and the adhesion between the chip and the tool is higher. It causes why? Because due to the high temperature, higher wear rates, and the shorter tool lives affect form the dimensional accuracy and the subsurface structure. These are the main disadvantage, and there is a dust collectors is required to protect the operators from the any dust, right? And this is the minimum quantity lubrication one. Here this is the drilling. For the drilling operation, we can give the drilling operation to a minimum quantity lubrication. This is the compressor, and this is the pneumatic, and this is the hydraulic, right? Here the oil is supplied at the supplied from this one end, and air is supplied from the one end, and this is the air and the oil. Here it will be formed and it will be mixed into the one mixing chamber. This is the end mill cutter, isn't it? And at the proper place, here this mixed oil, here it will be supplied. This is the one experimental setup. One experimental setup. He has the this minimum coolant oil supplied, and here I have taken this one snapshots. And here they are supplying this oil, that is the 0.2 milliliter per hour, isn't it? And he has taken the reading up to the 500 milliliter per hour. Here this is the one, right? Here this is the one again advantages of this this cooling. Here see, this is the one nozzle. And these are the two options for the drilling. Hello, sir. BC, sir. Hello, BC, sir. Okay, see, this is a cheap section installation. That is the how to evacuate the chips. That is the swell arm and the pipe balancer, automatic paste trap, the exhaust nodes, then the ejected chips, and how to here the chip disposer to break down the chips. Here the chip extractor is there is a combined unit. These are the dry machining methods. In the near dry machining method, near dry machining, that is the 20 to 100 liter per hour. Here the maximum, that is the but in machining center, but in minimum quantity lubrication, that is a 0.08 liter per hour. Maximum, that is a 0.21 liter per hour. Here, these such types of this oil, it will be recommended. This is the minimum quantity lubrication and minimum quantity coolant system. These are the again two parameters, MQL and MQC. MQC means what? Minimum quantity coolant system, and MQL, that is the minimum quantity lubrication system. Cooling and the lubrication, these two different units are provided, and the and the lubricants that is the we are using, that is the vegetable oils, non-toxic, biodegradable, to reduce the friction and the adhesion between the workpiece and the chip tool chip, and MQC, that is the minimum quantity coolant, and here this minimum quantity lubrication media is used. Next, that is the here I have taken this one advertise from this Dropsa. Here I have taken this one complete. This is operating result. They have manufactured one unit of this mixing elements, mixing of this air and this oil. See, this unit is operated by the electro-hydraulic valve. This electro-hydraulic valve, and this is the oil delivery regulator. This is the flow compensating valve, and this is the air and oil outlet, and this is the fixing for the other elements. Okay, and this is the flow compensating flow control. This flow compensating flow control wall. Here the what will happen, the this flow regulating wall, here it will be moves and up and down. Then what will happen, the when pressure at the system side, when it will be increasing, and then oil flow, maximum oil flow, it will be supplied when when there is a minimum pressure at the system side, the minimum oil flow, it will be supplied towards the system. That means minimum oil, maximum oil, minimum pressure, maximum pressure. Here the pressure when it is increasing and decreasing, and the oil flow here it will be decreasing and increasing, and here the flow compensating this flow control wall, here it will be used. This is the unit. This is the external unit for the machine tool condition, right? Okay. Here see minimum air oil micro lubrications. Here this is the one, it has the oil reservoir, air pressure display. There is a one unit. Electronic flow sensor is there. Why electronic flow sensor is required? Because here the to supply the proper amount of this mist flow, air plus oil. Here the proper and the proper air pressure, here it will be supplied, and the air and the liquid pressure, oil pressure, here it will be maintained, and multi-dispensing pump, that is the positive displacement pumps are used. That is the gear type pump or the vent type pump they are using, but probably they are using the gear type pump. This is the and air pressure regulator, that is the maximum 6 to 8 air bar pressures are used. Here, these are the technical features of these mist lubrication systems. Here it is connected at the end of this machine tool, right? Here again, this is the one model of this simple atomizer. This simple atomizer, here the oil it will be separate from this side, and in this side it's the air it will be separate, and the air and the oil here it will be mixed, and total through this nozzle here through this aerosol nozzle or the diffuser here it will be separate towards the machine tools. Here, this is the one again one graph. One figure, that is the this gas. Instead of this oil, this gas it will be supplied, and these additives are supplied. This carbon dioxide is also supplied. Carbon dioxide additives, and this active electro. This sensitivity controls are used. This is called as the high voltage power supply units, HVPS, and AMQCL control system, minimum quantity coolant lubrication system. Hello, sir. बोला की. Hello, sir. अरे मग आता हो, माझं सुरू आहे ना. माझं सुरू आहे, तुम्ही जेवा ना. हॅलो. आणि ज्यावेळी तुम्हाला स्टॉप करायचं असेल त्यावेळी फक्त मला फोन करून सांगा, सर आता टाइम झालेला आपला, आपण किती संपवायचं. नाही ठीक आहे. नाही तुम्ही जॉईन व्हाल त्यानंतर आपण स्टॉप करू, कारण 12 वाजून झालेलं. हो, मी कन्क्लूड करून टाकतो. ओके लगेच कन्क्लूड करून टाकतो, 5 मिनिटात. तुम्ही जेवला. बरं, मी 5 मिनिट कव्हर करतो, कारण 10 ते 11:30 लेक्चर आहे. कारण आता 12:05 झालेले, आपण तुम्ही जॉईन व्हा, 5 मिनिटानंतर आपण स्टॉप करून टाकू. ओके. See here, this is this carbon dioxide and the additives. Here it will be, and the gas it will be supplied toward the nozzle, and here this is the nozzle spray. It will be supplied toward the minimum quantity coolant lubrication systems. Here previously that is the MQL systems, but here the cutting tools, here it will be cooled, and the workpiece it will be cooled. And what will happen? The gases it will be evaporated, and this cutting this action takes place. Here, this is the main aspect, right? Here, this is the one electrosol spray is provided. This is the one gas film is there, and additive film is there. This carbon dioxide, and electrosol spray is provided to supply the air and the oil, right? And this is the advanced MQCL. This is the minimum quantity lubrication. This is the physical component and the chemical component. And here we can use the PTFE, so solid material, and the liquid material, that is aqueous solution, hydrocarbon, vegetable oil. Here it will be supplied ester, glycol, alcohol, sulfides. These are the materials are used. Here the surface finish it will be produced. Here this is the hot material. Okay, then okay, here this is the thank you for the listening of all the participants. Hello, sir. Hello.
Hello, sir.
Yes, sir. Thank you, sir.
Okay.
You have given this opportunity to me to give the this webinar for the expert lecture for the emerging trends in this mechanical engineering. Thank you to all, and your management committee, principal, and the head of the department of the mechanical engineering and faculty, and also to you, sir. Very thank you, sir.
Thank you so much, sir. You are giving your valuable time and valuable knowledge. Thank you, sir.
1 minute, sir.
Oh.
Sir, upon
Yes, sir.
with participant, can you open the video camera and then shall we take this one photo, sir?
Okay, fine.
This is the most important, sir.
Already, sir, I have recorded YouTube live, so I will share you this link.
Okay.
Then everything is covered in this YouTube live.
Okay, YouTube it is shareable.
Yes, sir.
Okay.
I will provide you that link so that this link can be you can be share with anyone.
Okay, sir. Thank you, sir. हरकत नहीं है.
Okay, sir.
Okay.
चालेल. Thank you, sir.
Okay, sir. Thank you. Bye.
Okay. Sir.
Okay, sir.
तिकडनं एंड करा मीटिंग कारण तुम्ही होस्ट आहे सध्या.
Okay. I will end.
एंड मीटिंग करा.
Okay.